Delicious with food is what he means. Good morning. I hope you've had enough of computers and humans over the last 2 days to let me talk to you about ants for an hour and a half, and enough coffee. So first, I want to say thank you to the LISA organizing committee. You guys have been so incredibly kind, and I'm so flattered that you asked me to come and give this keynote. So how many of you know what will happen if I put 50 ants on a table? Yes? Yeah, and then they'll just sort of, so what he said is they'll sort of spread out randomly, which is true, and then they'll pretty much walk around until they die of exhaustion. Now what will happen if I put 500,000 ants on a table? Irrelevant. So if I put 500,000 ants on a table, they'll start coordinating and collaborating with one another to find food or build a nest or form those like really amazing and like incredibly anxiety-inducing ant bridges, depending on what's in their environment. I find those anxiety-inducing. I don't know if any of you have seen videos of ant bridges being formed, but I always am like terrified that one of them is going to like fall, even though I know that they probably withstand a fall pretty well. So if you saw my TEDx talk, you knew the answer to those two questions. So this is a talk that I gave on how ants find your picnic basket at the end of my undergraduate degree at NYU. And Matt Simmons found this on the internet and asked if I would come and give a revival, and then asked if I would give a keynote-sized revival. And so here we are. And at first, I sort of oscillated from being super excited to being terrified to then being excited again. Because as he mentioned, that original talk was really short. It was actually under 10 minutes. And so really only time for brushstrokes for like a pretty heady topic. And so now, today I'm really excited because we have a ton of time and space to flex. So I'm still terrified, for the record. So I don't normally do this, but we do have a lot of material to cover, and I don't want to miss any of it. So I do have notes with me, so forgive me for looking down. So my name is Jane Adams. I'm a data scientist and a programmer, and I work currently at 2 Sigma. And my undergraduate research was focused on emergence in complex systems, and I was specifically looking at the role of phase transitions and phase transition dynamics in the emergence phenomenon. And so I was interested in how we might look at systems that are undergoing a phase transition as systems that are performing a computation, and if that might help us understand the scaling of information across levels in complex systems. So from there, I did a master's degree in urban data science, also at NYU, thinking that I would sort of continue my work with urban complex systems. So cities and neighborhoods, transit networks, these are really good examples of really rich complexity. And so I thought, okay, let's go study those, and let's dig into the many and myriad urban data sets that are out there. And so that didn't quite happen. Instead, what ended up happening is I became very interested in data in and of itself, the problems and the challenges and the difficulties of working with data, and how people are working with data. So that is a lot of the work that I do now. So if you follow me on Twitter, that's a lot of what you will see. And I'm not going to talk about any of that today. So if you want to talk to me about that, either find me afterwards or find me on the internet. So I've taken a couple of turns since that original TEDx talk. I feel like I've come pretty far in a short amount of time. But anyway, preparing this talk felt like putting on an old favorite pair of jeans. So anyway, ants are the bread and butter example of emergence in complex systems. So no individual ant has the instructions to find food or the information about where it is. Nor does any ant have the instructions to build a nest, nor the information on what features that nest needs to have. And even if they did, the way that ants communicate is not sufficiently rich to even communicate that information between each other. And no ant has any control over any of the others to enforce any of that behavior anyway. And yet, these behaviors emerge in ant colonies simply by adding more ants. So what is a complex system? And what isn't a complex system? What's emergence and what isn't emergence? That's what I'm going to talk about today. And my hope is that with a more nuanced understanding of complexity and emergence, we'll be better able to leverage the many biological analogs that we have for computational problems and implement solutions that have been honed and perfected over many evolutionary cycles in many different environments. So complexity is used to describe the behavior of a system that has a bunch of different parts that are all interacting with each other and their local environments. They're following relatively simple rules. So while the individual parts are doing that, complexity describes their collective behavior, how the whole system is behaving while each ant is minding its own local business. And so what we say when the individual, what we mean when we say that the individual components are relatively simple, what we mean is relative to the complexity of the whole system and what the whole system is doing. So, and this is going to simplify it a lot, but basically ants have pheromones. These are chemical signals that they sort of leave behind, and then they have antennae for sensing those pheromones. And then they have a limited set of actions that they can take based on the pheromone signals that they're picking up. And so the degrees, another way of sort of thinking about this is that the degrees of freedom of an ant are pretty limited. As is, sort of the amount and the quality of information that's available to them given their sensory capabilities. And so when we look at the whole colony, the actions that the whole colony can take are much more diverse. We see colonies building nests and foraging for food. These are the classic colony behaviors that I think everyone is familiar with. But colonies also engage in behaviors as complex as raising livestock and waging war on other colonies and burying their dead. So what's important to keep in mind is that each individual component of a complex system may be simple relative to that system, but it too could be a complex system whose behavior is complex relative to its component parts. So another good example of this is our immune system. So there are a couple of different levels to the immune system. First, we have physical barriers, skin for keeping bacteria and viruses out. But beyond the skin, we have what are called the innate and the adaptive immune systems. And so the innate immune system, what distinguishes these two things is the innate immune system has sort of a generic response to pathogens. It will sort of react to any pathogen in the same way, while the adaptive immune system has a more targeted, more personalized response. And it's the adaptive immune system that actually provides long-lasting protections against pathogens and provides immunity to us. And so both of these systems comprise cells. And the coordinated and distributed throughout the body identification of and attack on pathogens that these two systems do is way more complex than what the comprising cells are doing just sort of in their own local spot in your body. But that being said, the behavior of the cells, the individual cells, sensing their environments, actually like latching onto pathogens or however they do what they do, trapping them maybe, is complex compared to what the internals of every individual cell are doing, right? So I was on the train on Wednesday night coming up here. This is my first time in Boston. And I was sitting next to these two guys that were sort of creeping on my computer and saw what I was working on. To be fair, I was also creeping on them because they were talking about data. We really got into it. Anyway, so we got to talking, and one of them asked me, well, at what point does it bottom out? Like, at what point do the lower level systems stop being themselves complex systems, and you've just got like something simple? And I told him, I didn't really answer his question, and if any of you ask me that question, I probably won't answer it. Not because I don't find it interesting, but what I told him is that that's actually more of a philosophical question. And by that, I do not at all mean that it's not worthwhile, just for the record. I actually have a minor in philosophy. So it's more of a philosophical concern, but it actually raises something really interesting and really fundamental about complex systems, which is that you can totally take the lower levels for granted. You can give an account of the behavior of an ant colony without getting bogged down in specifics about individual ants. Those specifics are in many ways irrelevant, so we can abstract them away, which facilitates a lot of the research and study of complex systems. Like, this is what allows the rubber to hit the road in this research. So imagine that I'm trying to describe an ant colony reinforcing the mouth of its nest in advance of monsoon season, which is a thing that they do. It's certainly possible to provide a description of a colony and its behavior like exclusively in terms of what each individual ant is doing, with no reference at all to the colony as such. I could tell you the position of every single ant. I could like draw you a lattice. I could, drop ants all over it. I could, tell you the pheromone signals present at each position. I could give you some state transition function, some set of initial conditions at T0, and just like press play. And that description is huge. And I don't know if that description would actually capture what the colony is actually doing. If you would be able to tell, oh, this lattice is like reinforcing the mouth of sun nest in advance of monsoon season. And so what Stephen Wolfram showed us is that there are a lot of systems that are reducible in the sense that their behavior derives from the behavior of their component parts and initial conditions, but that providing a description of how such a system will evolve involves an irreducibly large computation. So this is called the principle of computational irreducibility. And what this means is that whenever computational irreducibility is present in a system, predicting how that system will behave requires, in effect, nothing short of going through as many steps in the computation as the evolution of the system itself. And so Another way of saying that is that while systems that exhibit computational irreducibility are ontologically reducible to the behavior of their component parts, in a descriptive sense, they're irreducible. So what we have with complex systems is a situation in which it's more efficient to describe a phenomenon in its own right, to describe a colony qua colony, than in terms of its individual component ants. So not only does this facilitate a lot of research, like I said, because you can imagine you could get really bogged down. It's a fundamental feature of complex systems that these tight layers of abstraction exist between the macro and the micro levels of a complex system. For all intents and purposes, the collective behavior is irreducible to the individual behavior. So it's not complexity if the behavior that the system as a whole exhibits is, to steal from Aristotle, which people in this field have been doing forever and ever and ever. Emergence is actually quite an old discipline. It's this old. It's not complexity if the system doesn't have features that aren't shared and can be described by the features of its component parts. So now we're starting to talk about emergence. Secretly, we've been talking about it the whole time. It's very difficult to talk about complexity without talking about emergence, and it's very difficult to talk about emergence without talking about complexity, but they are different, and they don't always appear together. But not many people appreciate what the relationship between these two things is and how actually sort of straightforward it is. So, as I said earlier, complexity describes the behavior. It captures the available information. It captures the sensory capabilities, the interaction dynamics, and the range of possible actions that a system can take. So complexity captures, again, these sort of degrees of freedom and the information available. Emergent phenomena are the actual behaviors, and emergence is the appearance or occurrence of those behaviors in a system. So, for instance, an emergent phenomenon that I mentioned already is an ant colony waging war on another colony. So that's the emergent phenomenon. Complexity describes the information from the environment and also from inside available to the colony, as well as the possible actions that the colony can and should take based on that information. So if the information is very limited, or if the behavior of the system isn't correlated with that information in any meaningful way, so either the behavior of the system is purely random, or no matter what the information is, the system always takes the same action, then the behavior isn't complex. And if the behavior isn't complex, we generally don't call it an emergent phenomenon. So some definitions of complexity, and there's no agreed upon definition. It's sort of like a you know it when you see it kind of thing. Some definitions require emergence. And in 1948, Warren Weaver, do we know who Warren Weaver is? He was a mathematician. He did much of the pioneering work in machine translation. He distinguished between disorganized and organized complexity to try to satisfy sort of both camps, both sort of definitions of complexity. So complex systems of both kinds have many parts that interact with each other. And the distinction between them is how you can describe the behavior of the whole. So disorganized complexity is well described by statistical mechanics, and organized complexity is not. So A good example of a disorganized complex system is a container of gas. So there are many individual parts interacting. We've got a bunch of molecules bumping into each other. And you can describe the behavior of the whole system more parsimoniously than you can by describing what each individual molecule is doing, right? So we're off on a good emergent foot. But the most parsimonious way to describe that behavior of that whole system is using is a statistical mechanical description, right? Effectively to sum over what all of the individual molecules are doing. In contrast, an example of an organized complex system is something like the marketplace. So here we have individuals providing goods and services, and we have other individuals consuming goods and services, and they exchange currency. That's their interaction. But when we zoom out, the dynamics of the whole system don't submit to a statistical mechanical description. So again, both of these systems, a marketplace and a container of gas, have a bunch of parts that are interacting with each other and following certain rules of what to do next based on those interactions. But only the marketplace's collective behavior we would call emergent. So, like, how does emergence happen? Is a really good question. We know that somewhere between 50 and 500,000 ants, complex collective behaviors start to emerge, but like, why? Like, what's that about? So in 1987, these three guys, who go by the acronym BTW, which is great, and they wrote like a ton of papers together. And they're just like referred to in the literature as BTW. And it dropped some like astounding research like in the field. And so it's so funny to be like, also like BTW, like this is a thing. So they published a paper in Physical Review Letters that first introduced the idea of self-organized criticality in systems. So self-organized criticality is the tendency of a system to evolve toward a critical point. Think a phase transition. So how many of you have seen a phase transition diagram before? Yeah, so you've got, on your x-axis you have temperature or pressure, and then on the y-axis you have phase regimes. So solid, liquid, gas, and so you see this slope, and then it sort of levels off for a bit, and then another slope, and then it levels off again, and then it keeps going up. So those points where it's leveling off, those are phase transitions, right? So water doesn't, for example, doesn't instantly or even smoothly transition from a solid to a liquid. Instead, there's this non-zero period of time where if you're looking at the dynamics of the water molecules, you can't rightly describe it as a solid or as a liquid. And this is what a critical point is. This is a phase transition. And the dynamics of the water molecules in those weird spaces are referred to as critical behavior. They're referred to as critical dynamics. So a lot of my work was looking at, okay, like what is it about those dynamics that might facilitate computation? Sort of taking inspiration from this guy in the 70s named Christopher Langton. So I'm not gonna talk about that, but cool dynamics, they have features, probably have consequences. So there has been really interesting work in the field of complex systems to describe these systems as the kind of systems that persist in these critical states. And another way of saying that is that people are trying, and they've had a lot of success in describing complex systems, or have had a lot of success making the case that self-organized criticality is one of the mechanisms by which emergent phenomena arise in nature. And so the difference between a critical point in water and a critical point in an ant colony is that the only way to achieve that critical point in water is to carefully tune a parameter, right? The temperature or the pressure. In a self-organizing critical system, critical states act as a sort of attractor. So as the system evolves, as we add more and more ants, it's evolving toward that critical state. And so self-organizing critical systems, once they reach those critical states, this switch gets flipped and they become resilient to like any more perturbations, the very perturbations that sort of drove them to that critical state in the first place. In our case, more ants. So with water, if we keep increasing the temperature or the pressure, eventually it'll complete its phase transition, enter the next phase regime, and then, if you keep going, it'll undergo another transition. But in a self-organizing critical system, once they get there, they just stay there. And so at this point, the system's behavior, the dynamics that it's exhibiting, are no longer correlated with the individual components. You can keep adding more ants, and either nothing will happen, or a child colony will split off, or the whole colony will perish. And so it's in this sense that the colony has emerged, when its behavior is no longer correlated with the introduction of more ants. Okay, what have we got so far? We have relatively simple components bumping into each other, minding their business. We keep adding more and more components for them to interact with. And at a certain point, a collective emerges. And that collective starts interacting with its environment, starts behaving in ways that are more complex than those of its constituent parts. But what we have to remember is that that complex collective behavior is realized only by those individual components, right? We haven't added anything new to the system, just more ants. The system remains decentralized, it remains distributed, yet manages to start acting as a single coherent entity. So this is the crux of what I want to talk about today. There's nothing to an ant colony above and beyond the individual ants and their interactions, really. And so ant colony algorithms for foraging for food and building nests and disposing of dead have to be very, very simple. Got a blank slide. There we go. They have to be implementable by actual ants, right? We don't have anything else to work with. They also have to be distributed because, again, there is no central authority or conducting ant in a colony. Does everybody know that this is true? Actually, people can sometimes be mistaken about this. So the queen ant is really just a worker that specializes in breeding. She doesn't have a global plan for the colony about what they're supposed to do and direct the other ants in making it happen. And in fact, given where the queen is positioned in the nest and how ants communicate with each other, that would actually be impossible. So again, the expression of ant algorithms has to be distributed. And finally, they have to be scalable to more and more ants, allowing the colony to grow and take in more resources, or to fewer ants in the case of a child colony splitting off. So you might notice that I've called out 3 features that we need our computational systems to have. That's not a coincidence. So let's consider harvester ants in the Arizona desert, because they've got a problem, which is that they have to spend water to get water. And they get water from the fats in the seeds that they eat, but they lose water while they're out foraging for food. Now, forager ants are actually like pretty hardcore. And so like if they leave the nest to find food, like they will not come back until they found it. It's a really like come back with your shield or on it type of situation. And so that means, again, because they lose water while they're foraging and outside the nest is dangerous, many of them die before they ever find food. Or more depressingly, like die while they're bringing it back. And this is more likely to happen in the desert on really hot, really dry days. So this biologist at Stanford, Deborah Gordon, she has studied harvester ants in the Arizona desert for like a super long time. Notice that these colonies sent out fewer foragers on really hot, really dry days. But it wasn't clear to her how that foraging was regulated. So the way they regulate is that each forager will wait at sort of this like narrow tunnel into the nest. And when another forager comes back with food, they'll sort of like drop their food off and then like touch antennae with the guys that are waiting. And then the guys that are waiting to determine whether or not to go out, they look at all of the interactions with returning foragers that they've had and like the timing of those interactions. And that's how they decide whether or not they're going to go out. So if there's food nearby, the interactions with returning foragers will be frequent, and there will be many of them. And if there's not food nearby, those interactions will be infrequent, and there won't be many of them. And so no single ant is making the decision to ramp up or ramp down foraging efforts. But collectively, they're all sort of making a decision about whether or not it's safe to go outside, or whether or not it's worth it to go outside. And so just this very simple interaction of touching antennae governs a pretty sophisticated and pretty advanced collective behavior of finding food and adapting to changing conditions. So what are these ants doing? I know some of you know what they're doing. I know you know. They're doing TCP. I'm not joking. So I don't think I need to explain what TCP is to this group, and I bet I'm like the least qualified of all the people in the room to do so. But like for the sake of posterity for the video, does somebody maybe want to hop up to the mic and give it a shot for me? Please. What's your name? Tom. Oh, you had the Tim Tams. Thank you so much. No, you did not have the Tim Tams. Mike had the Tim Tams. Are there Tim Tams to be had? Mike had the Tim Tams. I just spilled the beans.
The most simple explanation I would give is you don't send a packet until the last packet was successful, and if packets don't come back, you slow down sending packets.
What's a packet?
In this case, I think it's an ant.
Thank you so much. Right. So machines on the internet need to send files to one another, and sometimes the network might fail or slow down, and it's hard for stuff to get through. So if a machine is trying to send a file and it's using TCP, it'll break it up into smaller chunks called packets. Maybe we should move to like recall them ants, rename them. And it'll send out some of those packets, and it will wait to hear that those packets have been received, right? It'll wait for an ACK, an acknowledgement that it's been received. And based on how many ACKs it receives and how frequently determines how quickly it will send out the remaining packets. And so I appreciate that there's a lot more to TCP, like error detection and things like that. But the congestion handling is sort of the relevant part to me and to the ants. So the analogy to harvester ants is like really good. Sending a packet is equivalent to sending out a forager, and receiving an ACK is equivalent to a forager returning with food and touching antennae. And so if many ACKs are coming back quickly, it represents high bandwidth. And if many ants are coming back quickly, it means there's food nearby. So there was this article published last year, just like arrogantly titled, "The Independent Discovery of TCP/IP by Ants." And it's like old enough now that I don't think I should sort of like rally you all to email Priceonomics and be like, what is this? But we really should rename it, because ants have been doing this for a lot longer than humans have. So another system that I want to talk about are Starlings. So has anyone in here seen a Starling murmuration before? Has anyone seen one in real life? Yeah, I want to talk to the people that have seen one in real life, because I haven't. So I have a really beautiful video. It's about 4 minutes, and I hope you will bear with me, because it is important to sort of really see the collective behavior that I'm about to talk about, and to sort of appreciate how incredible it is. And you can ooh and ah. So someone asked me last night if I was talking about European starlings or African starlings, and I don't know. I think that's a falcon, by the way. Oh, this is where it gets really good. Look at that consensus. Okay. So that video was filmed by a wildlife videographer named David Winter, who I love the name of his website, and I also think that the last anyone heard of him, he was sailing around the world on an 18-foot yacht. So the closest I've come, so I've never seen a starling murmuration in real life, and I need all of you to tell me where to go and how to do it. But the closest I've ever come was this art piece by Duke Riley called Fly by Night that happened this past summer in the Brooklyn Navy Yard. And so what he did, he had a couple hundred pigeons, which are my favorite animals. And if you follow me on the internet, there will also be a lot of pigeons. And he had a couple hundred pigeons, and he attached little LEDs to their feet. And then right around dusk, he flew them. And so what this looks like with pigeons is you have this long stick, and you sort of wave it in the air, and the pigeons will start flying. They'll form this cyclone. And these cyclones are like, I don't know what the technical term is, but they're incredibly, incredibly robust. And so the people out in Brooklyn that actually do pigeon racing will sort of whip up their pigeons and try to like steal pigeons from other roofs, which is really interesting and hilarious. So anyway, Duke Riley had trained these pigeons to sort of adjust their configurations based on some really basic whistling patterns that he had. So pigeons are incredibly, incredibly intelligent. They're excellent learners. Look no farther than the fact that they not only survive but thrive in urban environments to sort of appreciate that that's true. And so the audience, we're sitting in these bleachers, and these pigeons are just like flying above us, and it's getting darker, and they have these little LEDs on their feet, and they're like sometimes really close, like right on top of you. And we don't often have experiences of collective behavior, of collective motion like that. And if any of you are interested, I do have some photos that I took of that night on my like very unloved website, if you want to look at them. And so this past week, as I was preparing for this talk, really one of the only things that brought me much solace as I was starting to properly panic was to see pigeons flying together. Just sort of like on their own around the city. Sort of look out from my desk and like see a little bit of emergence happening. There's actually a coop really close to my office, so that's a blessing. On one of the roofs close to my office. And so the thing that's breathtaking about Fly by Night and about a starling murmuration is how all of the birds move so quickly and so dynamically together. In other words, they achieve consensus about direction and speed almost immediately, even in highly uncertain environments. And it's important to watch, for those of you that haven't seen a starling murmuration, like it's important to see really how quickly it happens. It looks like you're looking at a fluid. And so starling murmurations almost always occur when there's a falcon near the edge of the flock. So falcons are predators, and much of a murmuration, a lot of that movement is the flock trying to put distance between itself and the falcon. And how they're able to move so gracefully, so swiftly, and also so synchronously is through what's called scale-free correlation. So scale-free correlation refers to a situation in which the correlation length, this is the distance between two, like how far away actions are correlated within a system, scales linearly with the size of the whole system. So if the flock is bigger, an individual starling's behavior will be correlated with a starling farther away from it than if the flock was smaller. And so when one starling changes direction or speed, every other starling in the flock responds to that change, and they do it nearly simultaneously, again, regardless of how big the flock is. So basically, what's happening is information is propagating across the entire flock with almost zero degradation. And this greatly enhances what's called the effective perceptive range of each starling. So basically, a starling on one side of the flock is able to respond to what starlings all the way on the opposite side of the flock are sensing. And this is what allows them to move like that. So how do they do it? How do we get that? How do they achieve scale-free correlation and such a high signal-to-noise ratio? So it turns out that each starling is continuously integrating messages from its 7 nearest neighbors. And what's weird is that 7, that number is the number regardless of how many birds there are in the flock. So from flocks of a couple hundred to over 1,000, that number is almost always 7. Sometimes it's 6, but overwhelmingly 7. And a paper was published in the Public Library of Science in 2013 that tried to answer, okay, like why 7? What is the combinatorial optimization problem being solved that 7 is the right answer for, is the optimal solution for? And it turns out that what 7 maximizes is robustness. Robustness refers to the ability of the flock to achieve consensus in the presence of uncertainty. And so what's important to keep in mind is that achieving consensus isn't the only thing that starlings need to do. They also, each of them needs to constantly be monitoring their environment for predators, for food, for roosting sites. And birds have a pretty limited, they have pretty limited capabilities around tracking multiple objects. So this is how cost is introduced into a starling system. So the number 7 appears to be the optimal solution given each starling's ability to track, or limited ability to track multiple objects. The solution is in terms of their limited capabilities. Again, this is a solution that is implementable and respects and honors starlings. It's local, it's decentralized, it's distributed. It doesn't rely on the directions from a single starling to reach every other starling in the flock, but rather it relies on all messages from all starlings to reach all other starlings in the flock. And regardless of how many starlings that might be, each one only has to pay attention to its 7 nearest neighbors. So harvester ants haven't been controlling congestion using TCP for all time. And starlings haven't been integrating messages from their 7 nearest neighbors for all time. Those solutions were yielded over many cycles of evolution in many different environments, in many different ant and starling populations. And so we often think about, now that we're talking about evolution, we often think about reproductive success in terms of the survival of the fittest, in terms of the individual. Fitter individuals within a population will experience greater reproductive success, and their traits, will be passed on and survive, etc. And so there's this idea in biology that the amount of food that an individual obtains is a proxy for reproductive success. And so what's amazing is that Gordon's work, again, Gordon is the one who studies harvester ants in the Arizona desert. Her work provides some of the first evidence for natural selection for not individual behaviors and traits, but for collective behaviors and traits. And what natural selection is favoring isn't going out and getting the most food. It's favoring colonies that hold back when conditions are unfavorable. So she found that the harvester ant colonies that tempered their foraging on really hot, really dry days experienced greater reproductive success than those that didn't. So this behavior, how colonies regulate their foraging based on environmental conditions, is also heritable. Child colonies, which are established far away enough from the parent colony that they'll never interact, will respond to extreme conditions in the same way as the parent. Parent and child colonies will make the same decisions about when to ramp up and ramp down their foraging in changing conditions. And so that's just amazing to me. And I see that as just further evidence that emergent collectives are entities in their own rights and need to be treated as such. So we have many biological analogs for computational problems. These aren't, I don't think any of these ideas, maybe some of the specifics are new, but I don't think like the idea of complexity and emergence is a new idea in these spaces at this point. And so we talked about ants and congestion control and starlings and consensus. Plants and schools of fish are also really good examples of consensus. And the differences, it's not the number 7 in fish, and there are some interesting distinctions between those systems and their environments that sort of explain that. That's some really interesting research. But some of the analogs that we didn't get to talk about, slime mold and network routing. Slime mold is also rad. Swarms, including ants, and distributed search. Neuronal spiking and probabilistic inference. Fly brains and max independent sets. So we know that biological systems provide analogs for our computational problems, but that hasn't translated into computational solutions that are truly biologically inspired. The exception would be like classes of ant colony optimization algorithms, sort of like ant alternatives to gradient descent, et cetera. But not, for instance, in our distributed systems have we really sort of like taken the torch from biology. And so one of the reasons for this is obvious, and we've discussed it already. Biological systems yield these optimal solutions over many, many, many cycles of evolution. And to build computational systems that are inspired by biology, we can't just look at the solutions and try to apply them to computers. We must first understand the evolutionary and environmental pressures that make those the right solution for that system in the first place. And these are the terms in which we need to be thinking about and making decisions about which biological algorithms we want to be implementing. So there's also the problem of representation. This is specifying all of the relevant aspects and how all of the relevant parts interact. And this is difficult both in modeling complex systems and in working with computers. For a computational model of a complex system to run, you have to, like, every aspect of every component and their interactions has to be well specified. And so this means specifying what actions a specific part can take, the conditions under which they take those actions, The information available to them, how they use, how they integrate and use and act on that information, what other parts they interact with, how, when. If all of these parameters are well specified, computational models can actually provide really deep insight into these systems. But it's difficult to specify all of those things well, even with something as simple as an ant. So identifying the abstractions, that's always a problem, is really hard. It's really hard with ants, as it is with computers. And so there's a last piece that I wish I had had more time to discuss, because it gets really fun. But the final complicating factor that I want to talk about that can make it difficult to take biological solutions and apply them to computers is that once the collective emerges, it introduces often top-down feedback into the system. So an example of this comes from the early days of the internet. So in the beginning, people were making web pages and linking to other web pages. And one of the early criticisms was that there was content out there, but like if you didn't already know the web address, like how were you supposed to find it? And if you did stumble across something, like how did you know it was the right thing, or like the best thing, or like the most relevant thing? And so what Google's insight was to take the linking behavior that was already happening between web pages and to use it to rank those web pages. So when you searched for something on Google, the top result would be the page on that topic that had the most other pages linking to it. And so again, this is classic emergent behavior. No individual user determines what the top result is going to be, and yet, like, every user determines what the top result is going to be. And the important piece is that it doesn't stop there, because the top result on Google is then more likely to be linked to by other web pages than something like buried on like the third or fourth page. And so nowadays, there's obviously a lot more that goes into the top results on Google and a lot more personalization. But there is still that top-down influence where we're more likely to click on, to link to cite elsewhere on the internet higher ranked Google results. And so not only is representing the individual components and their interactions and the information available to them very difficult, modeling the top-down feedback of the whole system back into those individuals is even more difficult, and in no small part because the interaction between the individuals and the whole system is nonlinear. As the system influences the behavior of the individual parts from the top down, the changing behavior of the individual parts gives rise to different collective system-wide behavior. So web pages link to other web pages, pushing a page up to the top of the Google search page, and that top result in turn coerces more and more web pages to also link to that result. So I don't think I've seen in the operations realm anyone trying or even sort of remotely relying on top-down feedback to control systems in this way. But if any of you have examples or ideas about what this might look like, I would be really interested. So to sum up, and I may have gone a little fast, but that will leave plenty of time for questions. It's hard. There's a lot going on in complex systems, and while the setup of complexity and emergence is actually quite simple and relies on only a couple of pieces to be in the right place at the right time, simple and abstract enough, in fact, for these incredible phenomena to show up all over nature across many different scales. That simplicity and abstraction gives rise to an incredible diversity of systems and behaviors. And that's difficult from an operational perspective to handle. But simplicity and abstraction are something that we do and should strive for in our software and in our systems. But in striving for it, we have to understand what the consequences might be of doing that well. Understanding that means determining if our systems are evolving toward critical states or if we might be pushing them toward critical states. It means determining if our systems exhibit organized or disorganized complex behavior. But most of all, it means recognizing an ant in a packet and a starling in a database. Thank you.
Hi, are we on? Okay, that was awesome.
Thank you.
Thank you so much. Okay, so my first question, if you were to, I guess the overarching question is, do ants maintain state? But if you had an ant colony and the ants were currently reinforcing the mouth of the nest for the oncoming monsoon season, and you added another 100,000, 10,000 ants, just drop them in, would they then begin engaging that behavior when they shared pheromones with the other ants, or would they have to like go do ant things first and then like figure out?
Well, so it totally depends. So again, one of the things that I mentioned is that once the colony emerges, the behavior of the collective becomes uncorrelated with the behavior of any individual ant. So like if you keep adding ants, you can't predict what's going to happen. And so they could like jump in and start participating. It also depends on what kind of ants they are. Like if they're workers or foragers or those kinds of specifics, they might cause the colony to split. You know, the whole colony might die because they can't feed and sustain that population. But the point is that you'd have to experiment with that in order to answer that question, I think. Yeah. You.
Yep.
Hi.
You. Niall Murphy from Google. I guess, actually responding to your previous point, when you add a whole load of ants, the behavior must go chaotic, right? It bounces around. Don't know where it goes. So I guess my question is, coming back to your point about if you have a colony and you have a child colony and they end up behaving in the same way. So that doesn't seem strongly correlated with heritability necessarily. So there's some runtime state that moves with the child colony. Does that imply that if you chop the child colony in half and add different ants from different colonies, you get different consensuses, if that's the word?
So I might have been a little bit not careful enough in my wording when I say the same behavior. It's not the exact same, but they again they're likely experiencing different environmental changes. But child colonies will they'll have like similar thresholds for or they'll sort of like ramp down their foraging and ramp it up in ways that are very similar to the parent colony. But the point, I think you said you didn't understand what that had to do with heritability, but what's important to keep in mind is that there's no individual ant that encodes that information about when to ramp up and when to ramp down. Like it's it's a collection of ants that has that. And so for a collection of ants to break off and still have that, that's like the heritability piece. Is that fair? So if you chop it in half, you'd be leaving one half without a queen, which, assuming that it would persist even in such a scenario, I imagine that the behavior, that it would still behave quite similarly to each other, that they would not go out and forage as much on dry and hot days as others.
Okay. The other observation I wanted to make, which is towards the tail end of your talk, where you say there's a lot of interesting emergent behavior in biological systems which we don't seem to be taking advantage of in the computational realm. Like, part of the reason for that might be, like, it's obviously a lot more complicated. It's very hard to get right. If you get it wrong, it spins out of control, destroys your data center, sets everything on fire, takes over the world. And it's kind of much simpler to iterate over a loop and do your stuff. You really, I think, to be properly inspired by biological systems, do you need a kind of hostile environment for that kind of robustness characteristic to really be relevant?
Well, so computers do exist in hostile environments, right? I mean, I think they do.
Well, I'm certainly hostile towards it.
So there was a section that I didn't have time to include, that was about, how do we compare the threat and risk and failure models of biological systems versus computational systems, because that definitely is like part of it. Part of deciding, like, okay, like, will 7 work for us, is part of understanding, okay, like, what is the predator here, and like what's going to happen if the predator gets us? What kind of collective behavior do we want anyway? So I think that we don't need to introduce a hostile environment. We just need to better represent the environment that our computational systems already exist in, and figure out how that maps onto nature.
Interesting. Yeah, I think of genetic algorithms in this case, but they haven't been quite as successful as machine learning in general case.
Actually, some ant colony algorithms are more effective than genetic algorithms, which I find very interesting.
Thank you very much.
Thank you.
Go ahead, you're ahead of me. My name's Hugh. I'm from OpenDNS. Fascinating talk. I've got 900 questions, but I'll ask one. You've described behavior that emerges from simple actors, but only when they sort of achieve a certain critical mass. So 50 ants in a table do this, 500,000 ants do that. Presumably the same is true of other behaviors you've described, starlings, pigeons, fish, and so on. Are we aware of some generic property that causes these more complex behaviors to emerge at these numbers? Like, is there something we can look at where it's like the output of an equation where, yes, it's not 50, but 923 ants will behave this way? Do we have any good handle on that?
Are you asking about a threshold?
Yes.
Yeah.
Thank you.
So there is no threshold. I know that that's super unsatisfying.
That's super
and
unsatisfying.
People are like, okay, like, is it the 501st ant? Like, the 502nd? So these are self-organized. I've given examples of self-organizing critical systems. So as we keep adding elements, they're driving toward these critical states. And the addition of which element like tips it over is, it's just not a fixed number. And it's also different in different systems. So I'm sure that since the last time I looked into the research on thresholds of complexity, people have made some sort of progress on this question. But the last I heard, no.
Thank you.
I have what may or may not be a relevant question about other background that you might have heard of. What you were talking about reminds me a lot of a section from Douglas Hofstadter's Godel Shabak with Aunt Eater. And I was just curious if
Aunt Hillary?
Aunt Hillary, that was it. Aunt Hillary. And I was just wondering if it was more than if there was more than an amusing relationship between what he discussed there, where he was talking about the emergence of intelligence, and from what you're discussing, I don't think you think starling murmurs are demonstrating intelligence, but I'm wondering if there's any relationship in what you might know of that.
Yeah, there absolutely is, and Douglas Hofstadter has been really influential in my work, that book especially, and so I picked the systems that I did, namely ants and starlings, because they're pretty tractable. Intelligence is really, really hard to get into, but what I hope everyone walks away with is that, like, these kinds of things happen at many, many, many different scales, ranging from, like, the very concrete, like actually physically implemented, to abstract levels like cognition, and sort of wetware like the human brain. So yes, absolutely. I did a lot of my undergraduate work was sort of used his work on cognition and percepts as like a jumping off point.
Thank you.
Colin Hinks from Edinburgh. Near the beginning of your talk, you talked a bit about phase transitions. In a deep, dark past, I was a physicist. We have some of those. Things like water, the universe, cake has them. But one thing that's fairly universal about the ones that at least I'm aware of before is that you talk about those plateaus where you have those phase transitions, and in those areas, you're kind of almost always increasing the energy of individual things in the system, but it's not changing its behavior until it comes out of the phase transition. Is there it doesn't seem that when you add more ants, you're changing the energy per individual or anything that's quite so kind of the same as those physical phase transitions. Is there something that's equivalent?
Well, so I guess it seems sort of obvious to me that adding ants is like adding more energy to a system.
To the full system, but not per individual ant.
Pardon?
Well, you're adding more stuff to the full system, so more energy to the full system, but it's not more energy per unit.
Might not be appreciating the distinction.
So when water goes through its phase transition, you aren't adding any more molecules, but each molecule gets more energy. And when space-time kind of changes and you get the strong and the weak force.
Yeah. So I would say that in ants, I have not thought about this before, but on the spot, my thought is that there are positive returns on being part of a larger collective that correspond to an ant being like more efficient or to better use resources, and that would be sort of the analogy there.
Okay.
But I haven't thought about that. Thank you.
Okay. I have my suspicions.
Yes.
Hi there. I have a question in regards to the way that stimulus or external stimulus is applied to a complex system. So, for instance, in order to create the murmurations with the starlings, you have usually the falcon that's at the edge, and then that creates the process for them to go through the murmuration. And I'm wondering if there's any way that an analysis of the external stimulus to the way that the murmurations have been done, or something similar to that is done in the same way that you look at a fractal set, and different algorithms would be applied to create certain end states. So if you have one type of external stimulus to a complex system, is that actually repeatable, or is there an algorithm that you can see what state the complex system is when you apply that stimulus to it?
Yeah, so that's a really good question. The research on, I guess I don't have to lean over, but I prefer this microphone. The research that tried to ask, okay, like why 7 nearest neighbors in starling flocks, actually was done using data from flocks under normal, like murmurations under normal conditions, where there was no falcon present. Or, sorry, murmuration with a falcon present is like by and large the normal occurrence of a murmuration, but they looked at, they were looking at murmurations where there was no falcon present. And so the behavior, and so I guess like the distinction there they were looking at murmurations when the behavior is not like necessarily goal-oriented. And so it would be really interesting to see, when the stimulus introduces a goal into the system, how does it adjust the collective behavior differently than when there is no goal introduced by an external stimulus into the system? So I haven't read any research on trying to distinguish between murmurations with or without a falcon present, but my sense is that depending on the system, that actually might make quite a large difference in the collective behavior and the collective response that you see.
And just one thing I'd like to know is that I think it would be interesting to look at the system itself that has been affected, and disregarding what the stimulus is, and then try to determine what the stimulus is based on the resulting action of the complex system.
Yeah, are the dynamics enough that we can sort of predict what the stimulus was, or guess what it was?
That would be really beneficial in a computing environment.
Yes.
So, yeah,
definitely.
Betsy Schwartz, Tricore Solutions. You talked about computation. You talked about communication. The third thing I think about is storage. Can a system like this store information? Can a system, an individual system or colony, learn? And is that the same question?
Oh, that second one's really hard. So,
you don't have to answer it on the spot.
So I think there's also a third interesting question, which is, do they need to store information? Like, what do they need to store? I actually imagine, my hunch is that biological complex systems, are sort of like a lot more comfortable throwing away lots of data than we are. But if there's a learning element, how is the information required for that learning? Like, where does it reside? Especially when the learning is collectively distributed as opposed to happening in individuals. So is that the same question?
If the colony is built for the third season shoring up their door, are they better at it than the first season?
If they're, sorry, could you repeat that?
What were they doing? They were shoring up the entrance to their tunnel?
Oh, yeah,
if they're doing it for the third
stronger.
season, are they better at it than the first season?
Yeah, they're still around, right? The most evolutionarily successful species on the planet. So how sort of information storage and retrieval plays into that? I don't know on the spot, but I'm sure there are very smart people working on that.
Thank you.
Yes.
This is too low. So, my name is Michael, and I was the instructor of interfacing with IoT which is the reason this is very relevant. Your research, very impressive. My question is, this is a long shot too. Not many know what game theory is. But it would seem relevant, and is it worth considering the emergent behaviors in nature to maybe improve systems based on game theory?
Yeah, so it depends on, so game theory isn't relevant in all complex systems, right? There has to sort of be, you need the components and you need their interactions to like satisfy a certain set of criteria for game theory to sort of well describe how they engage with one another. So ants maybe not, but once you get into more, like especially more human systems, economic systems, social networks, business networks, like things like that, absolutely, it absolutely becomes relevant in how you represent the interactions of individual components.
Hi, I'm Eric Marshall from Rutgers University. This will be hopefully an easy question, but first, a really brief comment. I think you've answered an age-old question for all of us. Which came first, the software or the bugs? And the easy question, hopefully, is could you describe a few pointers into these topics, some starting points, a toehold? If I want to go home and pursue some of this, how would I do that?
So I know there's not a lot to my slides, so I don't generally distribute them because they don't really stand on their own very well. But there is a lot of research behind this keynote, and I was thinking of attaching all of the papers that sort of went into each slide, if that would be helpful for people. So my first is you said you're from Rutgers?
Yes.
So you read papers?
Occasionally.
Yeah.
I'm an IT guy.
So reading papers is a huge piece. I would keep track of the Santa Fe Institute in Santa Fe. They do. They're doing. They've got a lot of the people that are sort of like actively working on complexity right now. And then there are some good. There's like a pop science book. I don't know if you would be into that. There's a pop science book by Stephen Johnson, who I actually really like, called Emergence, like the collective lives of ants, cities, humans, and software, something like that. That's really good. And then there's another book called Complex Adaptive Systems that is quite good. But I'll get the papers. But otherwise, if you're looking for sort of like sort of easier than getting like deep into research papers, introductions to emergence and complexity, those two books I would recommend.
Excellent. Thank you so much.
Last question. Yep. Tom Gilman, EMC. It occurs to me that your diagram of the Starling murmur interconnectedness is remarkably similar to a cellular data network. Do you know if there's any studies that have been done on this correlation?
I don't know. And if there's not, are you capable of doing such a study?
Maybe.
So yeah. So actually, this is the last thing that I should have said. So part of bringing these biological algorithms into our computer systems is, many of us in this room are capable of doing research and writing research papers. And if you see a connection between two things, like, go try to prove that it's there. That would be amazing for both disciplines. Thank you all so much.